All right. This is sort of the takeaway slide in case you want to revisit this later. Now, what can we do with this? We can plot this into a roofline model. So again, quick show of hands, who has never heard of a roofline model? Okay. The idea is, in essence, you are looking at two different limiting factors for your performance, right? Memory bandwidth and computational throughput. We've discussed this now a couple of times. The way you can relate those is by capturing how many data you need to move per computation that you're doing. Or the other way around, how many flops can you do for every byte transferred? This gives you something that is called the arithmetic intensity. If that's really high, then you're doing a lot of computation for very little data transfer. If it's really low, you're doing very little computation but transfer a lot of data. And this is sort of what goes in here, I don't know if you can see this, on the x-axis. This is your arithmetic intensity measured in flops per byte. And then on the y-axis is your actual observed performance. And this is given in floats per second and in flops per second. And in this case, this would be 10 teraflops per second scaled. The reason why I'm a bit confused by this is just a screenshot from one of the tools that we will be looking at later that automatically sets up these roofline models. The reason I'm showing you this here is because you can set up this roofline model in a couple of ways. You can either use the theoretical limit, as we saw it in the datasheet. You can use your measured limits, or you can use the data that you actually obtained on profiling your actual application. And depending on that, you will get a bit of different effects. But in essence, you will always get a picture like this. So you're either bound by, so up until the ridge point here, and I will get into why there are two in a second. So up until this ridge point and everything to the right, you will be bound by computational performance. So this is related here to the peak performance of your GPU. You shouldn't be able to get higher than that. And sort of on that slope here, you're limited by main memory bandwidth. So you can't get the data fast enough into the execution units to do the computations. And in essence, your computational throughput then gets lower and lower, depending on how much more data you need to transfer. On that ridge point, sort of at the intersection of those two lines, you're at a perfect balance. You're using the compute to its full extent and the memory to its full extent. So this is in an ideal world where you want to be. Usually that's not possible because the arithmetic intensity is to a large extent dependent on your algorithm. And the ridge point is dependent on your architecture. So unless these two things magically match together, or you can implement it in a way that they do, you will probably not reach those, but this is fine. Now I said there are two, so usually you will see that in different variants. Here this is for single and double precision, so you will get different performance numbers here. In practice, you frequently also see roofline diagrams for L2 bandwidth, for L1 bandwidth, and for other factors as well. Okay, now this is sort of the, I don't want to say old school because it sounds wrong, but this is sort of an established way of approaching performance and showing whether your performance is using the or whether your code is showing performance and using the hardware the way it is intended to do. So the idea is you set up this roofline, you measure your flop rate, and you plot it. I don't know if you can see it, but there's this little dot plotted here right at this line. In practice, you will see three different possibilities. One, as we've just seen, the performance is exactly at the roofline. This is good. This is where you want to be. This means you hit a bottleneck. This means unless you change your code or your problem size or structure, whatever, you can't get any faster. Not on that hardware anyway. And this also gives you a hint where you want to spend your optimization time. So if you can shift that bottleneck, so let's say your bottleneck is computation, you could shift this by doing fewer computations. Sounds stupid, but maybe you can reformulate your algorithm to summarize some of the computations. If you're bound by main memory bandwidth, maybe you can find a way to transfer less data. for instance, by combining two kernels that write a result and just read it back in the next, and so on. And again, this is sort of it's good because this gives you a hint that you're already at the limit of your hardware. In rare cases, this can happen that you're above the roofline. So you're better than what the hardware should be able to give you. Usually this has one of two causes. One is you're not actually using the hardware bottleneck that you think you're using. For instance, if you rely heavily on caching, you might not be using the DRAM at all, or not to the extent that you think of. So you have no transfers to DRAM, which sort of either shifts your arithmetic intensity or the peak memory bandwidth that you have to add to your roofline. Or what also frequently happens, the compiler is clever, and you think you're doing a lot of flops, but you're not really. And if you're looking at this FMA, let's make this a bit more interactive. This FMA code here, for instance, and let's just say, okay, this is all good and well, but maybe I just want to time additions, because FMAs is not what I'm interested in. Let me just do something like this. Should be doing 1 million additions, right? Usually not, because the compiler is clever. The compiler figures out, well, 1 million times the same number added, I just can add that once and scale it by 1 million. And so in essence, what you will be doing is one FMA, and that's it. But you think you're doing 1 million operations. So your roofline will be skewed. It's also good because it tells you something about what the compiler is doing and what is happening in your application, but it's probably not what you want in practice. Okay, third option, sort of the one that is the most realistic, because you usually see that in practice. You're not at the roofline, you're somewhere below, and you have to figure out what is going wrong. All right. Now, a couple of performance issues that you have to look out for and that you most frequently encounter when you start profiling. The first one is a lack of parallelism. And we've also already heard, so the H100 has 17,000 execution units for a single precision floating point, meaning that if you can't do the 17,000 operations in parallel, you're not getting a peak performance. And you have to do this every cycle. And for memory, it's even worse. So to saturate the memory bandwidth, you usually need in the order of 100,000 threads, because the latency for a single memory access is super high on GPUs compared to CPUs. And by latency, I mean the time a thread has to spend waiting from saying I need that data until the data is given to the thread, in a sense. And there are ways to relate the memory bandwidth and the latency and the number of bytes transferred and so on. I don't want to go into detail here. Just want to give you a rough number. So this is in the order of 100,000 threads. And even better than giving you all these theoretical relations is giving you a tool to actually measure that. And we have a benchmark to actually measure that. We have actually two, one for the floating, for the FMAs and one for the memory bandwidth. So let's just use them and repeatedly apply them for different problem sizes to see what we need to hit our peak. Sort of technical details. So we're using the same code as I showed before. The script to do that is also included in the Git if you want to replicate this. And this has been done on the V100. Where's my pointer? No pointer. Okay, anyway, this has been done for the V100 32 gigabyte versions in bridges. This is important because they show a different memory bandwidth. And for an A100 80 gigabyte version. So this is the bigger version of it. Okay, what can we see? So let's just look at the flops and we can see something like this. If you're familiar with GPU programming and GPU performance, again, this will probably look a bit familiar because this is one of the early examples. What we see at the bottom is the number of threads doing computations. And what we see here is the sustained performance overall the GPU. And you can see for a good number or a good portion of that graph, you don't see any performance at all. And why am I telling you this? Because if you have a code and you know how many threads you usually have working on your problem, you can relate this to this graph. You can look into the graph and see, okay, for this architecture, for this problem size or number of threads, I'm expecting this kind of performance at the limit. So why is this important to you? If you have a really low floating point performance, and you see this in your roofline, for example, first of all, you have to figure out why you have that. And this could either be because you have some other bottleneck, or because your code is inefficient, or it can be because you have a lack of parallelism. So this gives you a realistic peak bandwidth that peak performance that you can compare with, in contrast to to this black bar here, which is the theoretical limit. Okay, another thing you can see, so I tried this for CUDA and OpenMP, so this is the blue and the red curve. You can see that these behave very similarly. You can also see that if you're from CUDA, my execution configuration is probably not the same as OpenMP's or what OpenMP have guessed, so that it's slightly different here in these regimes, and it's really different here. But in the end, the asymptotic sustained performance is the same. And you can also see that there are these little zigzags or dips here. Anyone has any idea how or why this could be happening? Yeah? Sorry? No, this is pure computation. So this is the FMA benchmark, and there are cache effects technically, but this is not what is causing this. One more. Yeah, exactly. That's exactly the point. So here you can see that the GPU is filled, ideally, let's say, and then you add one more team, one more block, whatever you want to call it, have one more SM doing the same work, and that all the other 100 SMs have to wait for that one to finish. To be precise, this is at 20,171. Sounds a bit weird. This is just due to the sampling that I imposed, which sort of follows an exponential function. Okay, and again, so this is sort of just below the 80 SMs times the 256 threads that I run on each of those. And yeah, per block. Anyway, for the A100, just to show you the complete picture, you will get the same effect. OpenMP and CUDA here agree more, so I just ran the same code, but OpenMP on this architecture, or the compiler using or translating my OpenMP code, thought that my execution configuration is probably a good idea, so this is why you see nice matches here. Hopefully you do. And you see the same dipping effect, and it is the same effect, but it's a different position, but you still can apply the same mechanism. So it's now at 26,000 whatever, but this is still related to the number of SMs. So you can really see a load balance effect in essence here in play. And again, these kind of micro benchmarks can already give you a lot of insight into what is happening in your code, even without using these fancy profiling tools. So this is just using timers and some Python wrapping around it. Okay, for stream, just to show you, you get a different effect. Let's say, okay, so this is the peak bandwidth on V100. So okay, it was not 900, but close to 1,000. Sorry for that. But in any case, you also see you need a lot of threads to actually make this work. And you see two more effects. So OpenMP does a little bit worse here. My suspicion would be that it chooses a bigger team size or block size and cannot fill the GPU as efficiently as what I arbitrarily choose for my CUDA code. And you see something that we usually call an L2 bump here in our graph. This is where we actually exceed the theoretical limit. And as I've told you before, if we exceed the theoretical limit, we're usually not using the resource that we actually want to investigate. And in this case, we're more or less measuring the L2 bandwidth with some restrictions. So the actual L2 bandwidth is probably a bit higher. But yeah, this is that effect here in play. Again, for you, this is relevant because if your problem fits into the L2 cache, or large part of the problem fits into the L2 cache, this is what you want to use because this is the bandwidth that you want to get with your application. Okay, and just to relate this again, so here this is about 350,000 elements. So if you combine this all together, this is about 5.5 megabytes of data that we are moving around, which is just fitting into the 6 megabyte L2 cache. So again, you directly see the hardware here in this chart. or the hardware characteristics. For the A100, again, just to show you this as a reference, you get the same picture. You get the same effect, but again at a different point. This is why this is important to repeat this for the hardware that you're actually running on. And here you get this way later at around 1.5 million elements for around 24 megabytes total volume. And again, here it's a bit tricky. So I said in the beginning for the hoppers and the amperes, the cache is partitioned into 2 cache partitions. And there's a more or less sophisticated protocol moving data between those. And you would expect to get the best performance just short of 40 megabytes total data volume, but you're getting is at 24 already. And this is where you sort of just exceed the cache partition, so 1/2 of it, but still fit in the total cache. If you're interested in this, I can probably talk about half an hour alone on those cache partitions. It's really interesting if you're involved in that, but for the rest, I don't want to bore you. So if you're interested, just let me know later on. That is a good question. So 2 answers. So one, to be fair, you've seen the code. It didn't tune the code, neither the CUDA code nor the OpenMP code. So the CUDA is sort of a standard, arbitrary, what I always write down, and OpenMP is just slap on some pragmas and let the compiler figure it out. So what can happen is that the compiler chooses different default settings for the number of threads and the number of threads per block and stuff like this, which heavily influence performance. And this changes from version to version. I wouldn't say it gets better, but it will be, or it can be different, because better sort of depends on what is happening. And for OpenMP, it doesn't know the problem size a priori. So either it does something clever at runtime, usually it doesn't, or it tries to find a solution which works good in many cases. So yeah. And you see this here. So the sustained bandwidth for OpenMP is higher at the end. So my way of implementing it is not ideal for this scenario. Here OpenMP does a better job, and here as well. So mine is working better in sort of the middle region, but the CUDA version is working better in the middle region, and OpenMP's version is working better towards the end. Again, in the end, always the same story. Take your code, profile it, see what the actual performance is like. All right. Good. So we already figured out about this lack of parallelism. The second thing that usually can go wrong on a GPU is a lack of uniformity. We've talked about this today already a little bit. Ludovic talked about this yesterday as well. Ideally, we want to do all the we want to have all the threads do the same operations at the same time. And there are 2 reasons for that. One is the computational side, and one is the way GPU transfers memory. And we will look at both. Let me just, sorry for that. Let me just bring up the code. You will have this in strided FMA and strided stream. Again, I'm showing you the CPU version. The rest is taking the same code, wrapping it with pragmas or kernels and stuff like this, doing some memory management, but yeah, performing the same operations. And here the idea is we loop over a number of threads. And let's say again our NX, or the number of threads or iterations or whatever you want to call it, is 1 million. We just multiply this by some fixed stride. This is a small number between 1 and let's say 32. Then we will read, and just to make sure that we read from the original array, we will read from I divided by stride. And then this is probably not the most ideal way of implementing it, granted, but it still works. And then we will introduce the branch that we're actually interested in. We will look whether our I can be evenly divided by stride. So if it's 1, this is always true. If it's 2, every second thread will go into that branch. If it's 4, every 1 of 4 threads will go into that branch, and so on. And then we do the same operation that we did before. So the only thing we changed was we increased the iteration space. So we're doing stride times as many iterations, but only every stride iteration we will actually do something. So the overall number of floating point operations that we do remains constant. I hope you can see that. We only change the way we distribute our computations in a sense. For the stream, it's even easier. We take the same amount of iterations, we still go from 0 to nx, and we're just modifying our access pattern slightly. We're just, instead of taking the ith element, we take stride times I. So again, the number of memory operations should be the same. The number of bytes transferred should be the same. We're doing the same thing, independent of the stride. Okay, hopefully that's clear. Otherwise, again, just interrupt me. Okay, so when we do this, first of all, for the FMA, we will get a picture like this. And I'll split this up into OpenMP and CUDA. One, to not give you the impression that I only show you one or the other, or favor one or the other, or hide some effects or whatever, but also to include multiple measurements, as you will see on the next slide. But for this, you see the same picture as before. So this is the same data as before. This matches what we did with the unstrided one, which we expect for a stride 1. So again, it's just a verification that we're doing the right thing here. Now we're increasing the stride, and we immediately lose half the performance. Why? Because I've said before, these threads in a thread block or in a team are executed in warps or groups of 32. And if half of the threads in that warp cannot do anything, the execution units scheduled for that will just be waiting. They'll just be waiting for work to be done. And this, in essence, means you have to wait twice as long, which means you can do only half the computational throughput. And not surprisingly, if you increase the stride, that gets worse. And worse, and worse, and worse. Okay? At some point, this will hit a limit in a sense. You can benchmark this as well, not shown here. And depending on the architecture, this limit will be a smaller or higher number, let's say it like this. And it also depends on the number of resources shared in a sense. Okay.
Why is it?
By factor of 2? No, that's a linear scale.
No.
Okay. Yeah, so admittedly a log-lin scale is probably not the best way of doing it, but it shows the effect very nicely.
I was thinking from 2 to 4.
Ah, right.
Double the stride, but then the difference is...
yeah, it goes from 8 to 4, so...
Yeah, exactly. In my head it was less. In my head it went from 8 to 6.
Ah, okay. I see.
Okay.
All right. Good. So for, where was I? For the execution units and the FMAs, that all makes sense, right? So we have execution units not doing any work, that's bad. We see those sort of holes or idle execution units, and we suffer in terms of performance. Again, why is this important? If your code shows such a pattern, then this is something that you can relate it to. Just to show you, for the A100, it sort of looks similar. You get a couple of other effects I don't want to go into detail with OpenMP. But on average, again, you're losing the same factors. Now, more importantly, about the memory bandwidth. And I'm just showing you the whole picture because you already expect this to drop. And indeed, it drops. Actually, it drops more than a factor of 2. Why this is, again, you can ask me later. That's a bit more complicated because it has to do with caching protocols and whatnot. But on average, you see the same effect. So the more you increase your stride, the more you suffer in terms of performance, and the lower your sustained memory bandwidth will be. You see the same caching effect. So this, whoops, for at least for CUDA, doesn't go away. For OpenMP, it was never there. So yeah, and just to, again, be complete, for A100, you get a similar effect. Now, the question is, why do you get this? Because this doesn't rely on execution units. This is a memory operation. So this should purely rely on the bytes transferred. So either we're transferring a lot of additional data volume, or we're doing something else, or the compiler is doing something else wrong at the runtime. And actually, we're transferring a lot of additional data that we don't want to. Why? Because we have something that is called a memory granularity or transfer granularity that has to be observed by the runtime. And that means you can, or you as a thread, cannot access a single data element. You have to access a chunk of data. And what the GPU expects or hopes for is something that is called a coalesced access. And you have a coalesced access when subsequent threads access subsequent memory locations. Then everything is fine, because this can all be bundled nicely in chunks. These chunks can be transferred, the data can be distributed onto the threads, everything is fine. So let's just, for the sake of visualization, say we have 4 threads accessing 4 elements, and the transfer granularity is also 4 elements. Again, you can transfer this in one operation, let's say, and you get the maximum bandwidth that we've seen before. If we have now a strided access, unsurprisingly, this doesn't work anymore, because you still have to observe this transfer granularity, but now you have holes. And you transfer data, which you have to, because you have to transfer the whole chunk, which you don't use, which none of your threads in your team or thread block use. So in essence, you're still getting the same bandwidth, but you're using only half of the data you transfer. So how this shows up is, well, you get half of the effective bandwidth. And of course, this gets worse. And at some point, you would expect an asymptotic behavior. So if you exceed the transfer granularity with your stride, then at some point you would expect this not to increase anymore. Because it doesn't matter that much how far these memory accesses are away. Again, why am I telling you this? Because this is something to look out in your code. If you have random access patterns, unstructured grids, writing to a histogram, stuff like this, you cannot expect, usually you cannot expect the full main memory bandwidth, and it might be worthwhile to think about techniques of getting closer to coalesced accesses. Because even if you have semi-coalesced accesses, this already mitigates the performance penalty that you're hit with. Okay, last bit of information here. What is the transfer granularity? Because I kept this explicitly vague. In practice, unfortunately, that depends. That depends on the GPU that you're using, and even worse, it depends on the level of memory hierarchy that you're currently at. So the transfer granularity from DRAM to L2 to L1 will be usually different. Okay. But again, just letting you know this, such that if you see this effect, you can say, I've seen this before. This is just a transfer granularity effect. Okay, so to summarize this so far, if your performance is quote-unquote not good enough, it's a good idea to first start by checking, do I have a sufficient level of parallelism? Do I have a high level of divergence in my inner kernel code or iterations? It's also usually a good idea, we saw this with the zigzag pattern, to try to vary your input configuration in terms of number of threads and thread block size and so on, to see whether you see a performance sensitivity towards that parameter. Because unfortunately, it can happen in practice that your profile, you see a really bad or really good performance, but you had just a really good or really bad guess. So if you vary this slightly, this gives you a broader picture, let's say. And of course, compared to the micro benchmarks we've talked about before, so memory and main memory in particular and FMAs are just one of the bottlenecks, could also be something different. If you did all of this and you still have no answer, your issue is probably somewhere else. And this somewhere else could be L1, L2 cache bandwidth, so this frequently happens. It could be something that is called L1 or shared memory bank conflicts. Don't want to go into detail here. Again, this is just a buzzword if you want to look it up later or talk to me. And of course, you have already heard of it, so that's good. And if you rely on atomic operations, again, for those of you who already use those, this could be effects of atomic congestion as well. And a plethora of other operations. As I said before, GPUs really are complicated machines, even though they look quite simple, and estimating the performance that you get out of those can be quite challenging. Okay, so questions so far before we head into the profiling tools? Sure. All right, so the question was, if I have a really powerful GPU and really powerful CPU, I'm paraphrasing, and I have a memory layout optimized for one or the other, it won't be performing good on, well, the counterpart. What can I do? In practice, to be honest, this is not so often the case, first of all, because usually if people buy big machines, they either focus on one or the other. And especially for clusters which focus heavily on GPUs, they try to get a more or less cheap or not so powerful CPU to keep the overall cost down. And your CPU is ideally not doing much anyway. If you by chance have a system where this is the case, you can do a couple of things. You could split your data layouts and handle the synchronization at the interfaces between CPU and GPU directly. That's a lot of coding work, but it works. You could, and this is something that I've done in practice as well, so I can tell you that it works. You have multiple MPI ranks and have some of the MPI ranks do only CPU and some of the MPI ranks do only GPU, and then leverage the MPI GPU aware communication to bridge between those two. And then you can choose the memory layout depending on which rank you're running on. And last but not least, you can do something similar, but combine this with something like Kuckuk, which gives you the flexibility to have one kernel on a specific data structure, which layout you can tune by means of template parameters. So you have just an ND array and instantiate this either, or not instantiate, but template this either to be GPU efficient in a sense or CPU efficient. So these are sort of the things that I would look into. But yeah, it's a hard problem. So first of all, you can just use your MPI data type. That works. You can do even a sort of communication inside one rank from CPU to GPU by specifying sort of a source and destination on CPU and GPU with CUDA. With OpenMP, it might be a bit more tricky, but that works. The problem is, again, since there are some experts in the room, correct me if I'm wrong, my latest experiments, which are 2 years or so back, showed that using MPI data types on GPU is a really bad idea, because the performance you will get is abysmal. I don't know what MPI is doing under the hood for the versions that I tried out, but it's not giving you any performance. Maybe they transfer, if you have a stride, every element separately in a single memory operation. I don't know. Maybe that would be a good thing to profile, but yeah. Okay, so usually, to sort of complete this, usually what I see in practice is packing the data on GPU and then transferring it in one big unstrided chunk, because this gives you an efficient transfer over the PCI, which is usually your bottleneck. So the packing is virtually for free. And if you fuse it with another kernel, it's even cheaper. All right.